Hello, everyone. Thanks for joining in our BRICS case study webinar. Can you guys all hear us? I assume that everybody can hear us. There is the Q&A session part. Okay, perfect. So throughout our case study webinar, if you guys have any questions, feel free to leave the questions on the chat, and then we'll try to answer those questions. And so that being said, it's one-on-one right now, so we'll start our case study webinar today. So the topic is about the concrete floor flatness testing for robotic facility building locations, right? So Kathleen, can you go to the next slides? So before we start our actual case study, we'd like to introduce us who we are. So we are from KCI. However, we are in our own product team called Bricks. Inside of the Bricks, we have many different platforms over here. So the Bricks is the AI machine learning platform that is geared toward to the AC industry. As you guys know, a lot of technology has been improving lately for our construction projects. And therefore, we as a BRICS platform would like to provide the AI machine learning geared toward to the AC industry. So as you can see here in the screen, there are different industries that we cover. Today, we'll be focused on the more of the surveyor group, which is called RoboFlat from our BRICS platform. And here is our mission, as you can see here. So we wanted to improve the workflow and also the safety at the construction site, and also improve the work flow in overall on it. So that being said, today we have two speakers. One is the Kathleen. She is our product manager, which is she will be talking about our case study. And then we have James Clay, who is the actual user of the RoboFlat, which is he'll be covering the more of the practical situation, how to utilize our output into the real workflow. So I'll be passed on to the Kathleen. And here we go, Kathleen.
Thanks, Jay. And hello, everybody. As Jay said, I'm Catherine Brill. I'm the product manager here at KCI. Very happy to talk to you today about our case study about innovative floor flatness technology. So it involves a warehouse owner. This company manufactures appliances, other physical goods. They were looking to streamline their operations some more by adding robotic systems to their warehouse facilities. So as part of that initiative, they're building a new, very large 600,000 square foot robotic warehouse, and they wanted to contract KCI as part of that overall building project. So the need to optimize efficiencies in facilities, whether it be warehouses, fulfillment centers, etc., it's really been on the rise as customers' purchasing habits have changed. I think it really got even worse with the advent of the pandemic, but now we all buy a lot, if most of our goods, online. And with that online purchasing, we also expect those orders to be delivered in a very timely fashion. And this stretches over to other industries as well. In the manufacturing industry, for example, they realize that they also need to boost productivity for their material handling. And I don't think it's too much of a stretch to say that robotic systems are truly redefining the way that we have traditionally handled logistics and inventory management. Robots can be beneficial in facilities in a variety of ways, whether it is material handling or order fulfillment or sorting or transporting goods. It's all can be done via robots now. However, with this new trend towards automation comes new considerations for actually the floor that the robots are going to be running on. So we found that concrete floors is critical to successful operations of robotic facilities because those robotic systems require much tighter floor flatness and levelness tolerance than your normal concrete floor slab. If a floor is uneven or worn, what happens is it has the potential to majorly disrupt the robot's navigation, could cause them to bottom out, could cause unexpected downtime or manual intervention. The results of that is more costs, so costs rise for building owners, and also it creates dangerous conditions for the workers that are in those facilities. The current state, however, of analyzing concrete floor flatness and levelness for these type of robotic facilities is time consuming, rather labor intensive, and oftentimes produces unsatisfactory results that lead, unfortunately, to project delays. So, for example, with the traditional way that data has been collected on these floors, it's typically used, mechanical device is being used, which requires someone to walk the length of the building and manually drag the instrument so that it's directly contacting the floor. It's labor intensive, perfectly great for smaller buildings and ideal for smaller buildings, but for large facilities, it's not feasible. Similarly, the traditional method for, once you've got the data, calculating its floor flatness and levelness can be complicated or resource intensive. So traditional solutions for testing produce hard to understand spreadsheet results, a bunch of numbers that don't really quite show exactly where on the floor the issues are, often requires specialized skills, calculating multiple measurements, so very manual, using a formula, even custom script development. The software testing solutions that are out there are desktop based. They take over that computer, take over the system resources, and requires expensive computers with high-end CPUs and high RAM capacity. So really our challenge was, how can we best deliver this service, this concrete floor testing analysis service to our client using innovative technology? Well, first we started with the way that we were capturing the data. So we used a 3D laser scanner to save time, increase our productivity. It certainly did. Laser scanners are so powerful because they can capture millions of data points in minutes very accurately. In our case, it took a day to capture that data versus it would have taken a week using a mechanical device. And once the laser scanner has collected the data, that point cloud data can be easily visualized, measured, and shared. We captured a snapshot of the conditions of the floor, but that is in now a 3D point cloud, which can be referenced when needed. So instead, if, for example, the benefits of that is if the floor changes, instead of having to physically revisit the site again, instead, we have the point cloud data available to be opened up and analyzed immediately. We also chose to add innovation to our floor flatness analysis using RoboFlat. So RoboFlat is a cloud-based solution for floor flatness levelness testing. It offers a unique patent pending approach for assessing surface deviations. It is computing the point cloud along with performing voxel grid geometry to analyze and look at the normal vectors, the point curvatures, the spherical coordinates, and the end result is that it's producing a very high degree of accuracy in its results. RoboFlat supports a wide variety of floor standards. So the standard test method for determining FF and FL numbers, which is ASTM E1155, RoboFlat does support that. Also supports TR34, which is the free movement standard. It has a variety of different floor classes that RoboFlat supports. And also RoboFlat offers custom settings. And we found this to be more and more a frequent requirement that robotic systems have their own custom specs for what their tolerances are. RoboFlat can support that scenario. So for this particular client, we captured floor data using a tripod scanner. We then uploaded the very large point cloud data file to RoboFlat, easily set up the test with granular tolerances, and then RoboFlat automatically analyzed the point cloud. And the results were very fast. You know, we leveraged the power of the cloud in order to test the floor quickly and deliver results, which included dynamic CAD files with precise guidance on where remediation needed to occur. Our output is very easy to understand. RoboFlat also provides the ability to customize reports and generate them for stakeholders. And also RoboFlat generates topographic maps, which highlight the floor deviations. So to get into more detail about what exactly RoboFlat delivered, I'm going to pass it off now to James Clay. And as Jay mentioned, he is the leader of our scanning services here, and he headed up the team that did this work for this client. So it's all yours, James. I'll stop sharing.
Okay, excellent. Thank you. Appreciate it. I'm going to share my screen real quick, and we can kind of go through the deliverables that we received back when we do run RoboFlat. And please, you know, if somebody needs to interrupt and there are questions, go ahead if you can. But it's kind of an open session here, just trying to walk through these for you real quick. But there might be questions. As one thing we tried to do with RoboFlat was have it return lots of information so that you can use it to deliver whatever your client's really looking for. And so I'm just going to go through each one of the files that comes back to the user and give you so you can get an idea of what kind of choices you have and also show you some of how we use it. So one of the first things, this is a typical of unzip the file that came back down from RoboFlat from the cloud after we had uploaded the point cloud. And the first thing you do, we can just take a look at the quick report that gets sent back to you in PDF format. You know, this information you filled out when you started using RoboFlat, you know, what was the name of your building, the site ID, whatever it might have been that you wanted to include in your report was filled out online in the product, and then it returns it as part of the report. And also you had put in what your tolerances were. Now it calculated the test dimensions and the start point based off what point cloud you sent up. But and then you also had selected the custom. In this scenario, we selected custom because the TR34 and the ASTM are, you know, their testing is limited as they don't provide also curvature tolerances. Now, some of this may not make a lot of sense to you, but when I show you the CAD file and our legend, it'll help some, which gets delivered automatically also. So just bear with me just for a minute. So as you walk through the settings, one thing is your total floor envelope. Often with these robotic floors, they'll want to know the entire floor. We only allow you allow the concrete deviation of in this case, 15 millimeters either side of zero of your finished floor design. And so with that, that's what we put in here, 15 millimeters. And the design finished floor, in this case, we left it blank. And so if you have a set of plans, your point cloud, and make sure that your point cloud is tied to that set of plans, coordinate base wise or elevation wise. And so let's just say that the finished floor elevation was supposed to be 100. Well, you should have used the local benchmark to tie your point cloud to, so your point cloud is in that range of the 100 around on the finished floor, and you would have typed that 100 in. In this case, the client said, "Look, we know our slab is close to our benchmark. We're not worried about that. We just want to make sure the overall deviation, because we're going to go build this hive system on top of it, and we don't want that overall deviation to be greater than 15 millimeters. So if you leave this blank, RoboFlat will automatically calculate from all the points the median point elevation across the whole floor, the whole slab. So it makes a best plane fit basically of the entire slab and says, okay, the median elevation of all your points there is what I'm going to use to test the 15 millimeter total deviation for. Then contour interval, you can put whatever interval you want there, and here's 3 millimeters. It's pretty tight, but that's pretty typical. That helps your remediation teams, the people, you're going to turn this whole report back over to the GC, or maybe even directly to the remediation teams that are working with they're going to go out and grind the floors. So they can use the contour map to help them understand where those failures are taking place or how the floor is shaped in that area to get it corrected. Then we test flatness, levelness, and curvature. And here, again, you'll see this in the legend, but we're telling how often we'd like it to test, what the overall tolerance is, and the grid sample size. So here we're doing a grid sample of 0.3 meters across the floor. So every 0.3 meters, we're going to test a floor flatness linear measurement of 0.3 meters, which is in floor flatness. And you'll see that in a minute is really times 2, 0.62, because you can take the middle point to calculate a vector to get the total deviation of 3 millimeters if it crosses that. Then there's levelness, 1 meter levelness. We tested it every 3 meters, but it's a 1 meter bar. Basically, you're laying on the floor and testing to see that it deviates from one of the other no greater than 9 millimeters in this case. And then there's curvature, again, a 1 meter span times 2, and I'll show you that in the legend, because it'll test 3 points to see if the floor is actually dipping and you have curvature. In this case, up to 8 millimeters. And again, it's projecting the first point through the second point as a vector and extends it to the third point, which is another meter away, and projects it to see if it's greater than 8 millimeters. And then part of the report there is what was returned. And the levelness test completed. There was 158,000 levelness tests completed. 572 of those failed the test. The levelness percentage was 0.36%, and 95th percentile was 4.90 millimeters. So a lot of times your client will say, look, I don't care if my floor fails as long as the 95th percentile is less than the overall tolerance. And so that's what we're trying to call out there for them. You'll see that a lot on floor flatness. And then curvature, same thing. How many tests were completed? 77,000, and then curvature test failed. So some of these will have more or less tests run depending on the size of grid you chose. And then if the test falls off the slab, it won't count it. Along the edge here, you may get a whole bunch of flatness tests that you're able to run, but the curvature test couldn't, because it's a full 2 meter test. It's 1 meter plus 1 meter, and it falls off the slab. So you'll get several rows that don't test for curvature in this case, the X direction, but along the Y, you will go all the way up to the edge. You'll get the Y test. Typical. This is just a curvature image that gets returned to you, which helps remediation teams. These can be included in your CAD files, but it helps the remediation team take a look at the slab, and basically as the normals curve across the triangles, you'll start seeing a deviation in the floor. And here there's not much, the floor is pretty flat, but you'll see that, and then this is a curvature bar colorized to help you find failures easier, or not find the failures really, but to kind of tell what's going on with the slab. And again, and then the other image that is returned, and this goes into your CAD file also automatically, both these images, for use as your part of your deliverable. But the overall deviation map. Now, like I said earlier, 15 millimeters was allowed either side of the overall slab deviation, and it took a base mean elevation computed off of the whole slab at 0.045 meters was the center point. And so anything that exceeded above the 15 meters or below the, I'm sorry, 15 millimeters, it will outline in blue or red. So immediately the crews go, okay, well, I know I've got to cut this down. I've got to cut these areas down. So that's just a quick look for, and this PDF here is really for your stakeholders that they can take a real quick look and see what kind of condition their floor in, how many tests failed, and what does that floor look like. So it gives them a real quick PDF version so that you don't have to have some specialized tool to open that up with. Well, I open so many. The next one is the full results XLS file. And in here, there's a little bit more power for you to run through each one of the separate tests. Again, a lot of that is repeated here of what we just saw in the PDF for each one of the different types of tests, what your settings were, how many failures there were, the 95th percentile, what the total deflections were, all those good things. But then right here in the center is one thing you'll run into. So this is part of the total deviation test for the entire slab, and those are all the points on the slab that were tested. We're looking at a side view basically of an X, Y, Z of every one of the points. So the Z is is running up and down the screen in your Y direction right this second. So that's the whole Z value. You see a blue line and a red line, and there's a green one embedded in there, which is the middle of the slab as per, again, back to what it calculated, 0.0045 meters for the finished floor elevation. And then 15 millimeters either side was represented by the blue and the red line. And the percentage down here below in this chart shows that 0.4% was higher, needed to be cut down, and 3.12%, which 10%, which is also over here, tells you here, and that slab was below. Now, the client may say, the client may say, well, what happens if we expand that to 0.02 for the overall tolerance? Well, this chart will update for you and tell you, okay, well, we're down to 0.004% failing. Now, none of these values will update on the left side because they're not tied to this automatic calculation. We want to try to preserve what was originally the test values. This is just to try to give. A lot of times the clients will come to you and say, well, let's go through some scenarios together. How can you get me some quick answers of what can we do about this slab? You know, if you increased it to 0.002, 20 millimeters, you're almost going to get a passing slab, is what that's telling. You can tell your client that. And let's just say that they also said, well, we rather do cut instead of fill. And here we've got some fill of 3%. So we could lower that by 0.00, like 4 millimeters, and then it will calculate the new fill for you, cut and fill, and tell you the percentage of cut and fill at that point. Now we've got 0.27% cut. I'm going to put this back to 15 millimeters. So now the cut has gone down to the, I'm sorry, the cut went up to 1.69%, but the fill has gone down to the less than 1%. So you can continue to move this down until you get all cut. A lot of times the client wants all cut, and it helps them understand it. And once you get that figured out, it's giving you new proposed finished floors up here as we move this elevation up and down. You can rerun this overall RoboFlat test with that new proposed finished floor, so that it will do the images we just saw. It'll remake those and everything so that you will have a brand new set of deliverables based off of that proposed finished floor that you can tell your clients, and give them that information. As we scroll down, also the finished floor failure, the levelness failures, and the flatness and curvature are all over on the left-hand side. But there's also the quick chart down here just to see, gives you a little speedometer and tells you what the 95th percentile was. Also, if your slab did pass or fail those overall. Also in the middle, this histogram at the bottom is still part of this overall floor deviation. Another good thing to look at is, okay, so where do most of the points fall at in the deviation? And so this histogram has stacked the points, gives you a point count of how many points fall within, in this case, of 4 millimeters and 6 millimeter deviation, and there's 35 million point or 355,000 point. I'm sorry, 35,000 points in that range. So it also gives you a real good look at to help your client understand what's really happening with the slab out there without having to have specialized software, just Excel spreadsheet. Then down at the bottom, we have a bunch of tabs. These tabs are heat maps, and we'll go to the one that will make more sense at first. So this is every point that we collected on the floor for the floor flatness testing, and every deviation that we caught. And so this slab was pretty doggone good, so you don't see very many failures. Or this heat map would be colored more red with a bunch of failures on it. You see as it starts to turn yellow or green or blue, it's getting further away from passing. But this is a quick way for your clients to take a look at their overall floor. And by the way, those big white spaces, they're kind of weird square shaped because of the shape of the Excel spreadsheet. But really, those are the columns. The columns weren't used as part of the calculations, obviously, and so you'll get those holes on the floor. But you can see around this column, we'll see some red failures there, and it does have the deviation stated in each one of those. One other thing you want to look at on the spreadsheet is over on the left-hand side and at the top, you'll get column names. This is the measurement routes of each one of the runs that were taken for the measurements that you see. So these names and also these are the coordinates, both correspond to your CAD file. So you can go through this whole file, all these tabs, and easily find your failures from here to your CAD file to help, more information. That's what this is all about. So, but back to the heat map. So this one's the overall deviation map for the finished floor points. This is your overall floor flatness failures. So we collect whatever size grid there was for your floor flatness. I think we said 300 millimeters. And that's what all these points are and how they compare to the overall slab deviation. Then the next tab, in the X direction, we checked for flatness. And you'll see all the pass or fails on those, or they weren't able to test because noise on the floor or something like that. And then also in the Y direction, we tested floor flatness. We also did curvature that way. And these are 2-meter tests, so you get some spacing in here. The runs are still based off of the smallest grid produced, so that you can correlate these from floor flatness, floor curvature, and find the same points. But these are 2-meter tests, so you'll see larger gaps in between where they were tested, however your settings were, and what the total results were here. Again, those meters spacing. You also have on further to the end the raw data. So the raw data that was extracted from your floor is posted here too, just in case your client wants the raw data or you want the raw data to do something else with. These are the grid raw points. So you can simply extract those and use them to test other things if you want to, for some reason. So that's a quick overview of this Excel spreadsheet. It has lots of information. And again, it can be overwhelming, but at the same time, it's there to give you the power to get the client the answers that they're looking for. The next one is the DXF file that's returned, and that will be the CAD file, which I've got on the screen now. And this is how it looks when you first open it up. And it's all fully layered so that it helps you break down the testing. So you could split this up into model spaces or whatever you want to do. Paper spaces. So you can deliver all the FC layers, that's your floor curvature. All the FD is your floor deviation for the overall slab deviation. All the FF is for your floor flatness. All the FL is for your floor levelness. And so you can shut those layers off in your paper space to help you give that quick deliverable. And then one thing also is a legend is always automatically produced. And this legend you can zoom into to help explain the testing that goes on towards your client. So here, floor flatness for concave floor flatness testing, we've collected these points across the floor. This is a profile view of the floor, and it shows how those 3 points are projected, and then the overall, and you can see that it says 3 millimeters was the test, and our length for our test was 300 millimeters. And a 300 millimeter grid, and it breaks it down there for you. And so if we go down to, like I was talking about curvature, we'll go look at the floor curvature, and The overall deviation was 8 millimeters, what we were testing, and we were testing 1 meter, which is 1,000 millimeters. And again, it was really 2 meters because you see we were collecting 3 points to test for that curvature. The dashed line there represents what the floor would look like, and then the 3 points that were picked up, which is standard curvature testing. Also, in this legend, there's a full explanation of how the test took place, and also symbology is called out so that so when you're drawing, when you're looking for, if you see a triangle and a red triangle, red line, then you know that's a curvature failure that has happened on the floor. So those, again, back to paper space, you put that paper space in your legend there that automatically generated, has your specs that you typed in automatically generated in that legend, and so you can just put it right on your sheet. So now I'm going to go through, I'm going to turn off some layers real quick so we can talk about something. I'm going to turn off all my layers, and then, yeah, turn off. I'm going to turn on our floor flatness layers. And here's your floor flatness failures. The number one, we'll zoom in and we're going to look at the top here so you can see that it does include the grid values that I was just talking about in the Excel spreadsheet. Notice the F for flatness, and then the Y grid, these are your runs that were taking place. So every one of these grid lines represents a run where we went down through there and we made all the measurements for your floor flatness testing in the X direction and in the Y direction. And those, again, correspond to your Excel spreadsheet, those X and Y numbers, and also the coordinates on the screen. You can see my coordinates scrolling down here at the bottom. Those are the same as on the Excel spreadsheet. Then, so what happens is, as RoboFlat goes through and it finds failures on the floor, it uses that legend and it will draw either concave or convex, and for flatness, concave or convex failures. And so here is a concave failure. If you select it, by the way, you'll see there's the layer. It's in a concave failure. This is the origin point, and that's the end point. And then there's also a small cut or fill, cut 0 millimeters. That's because you're right at the failure point. So you'll get those sometimes. There's zeros, and but we've rounded the decimals off because we're talking about the millimeter here. So we're very close. Again, this floor is very close, 0.2 millimeters. In some of these failures, but some get much worse, of course. We need to fill, so these are convex, so you need to be able to fill your floor 0.8 millimeters or 1.8 millimeters in this area. Let me do one thing also. I'm going to turn the floor deviation contours on. As part of the plot, let's just say that you were making your floor flatness plots. You can turn your contours on also, and it will help in that to give your clients an overall view of how how the floor kind of looks now. And look at there, you can see already by contour, there's a strange dip happening there. There's a hole right here in the floor. Obviously, we go 0, -3 millimeters, -6 millimeters, and that's why these are fills all in this area. So those contours will help with your remediation team, help them determine. We're calling out where the failures are, but it helps them understand when they get in there and look at those failures, what do I really need to do here to make sure we've given them a cut or fill values on the cuts or the fills here. And also the contours are showing, hey, look at that. I've got a big hill here and I've got a hole over here. So I need to fill here and cut there to get this floor flattened out. So useful information for them. And again, you can break this up into sheets to make sure they can see all that. And if we go back, we turn off this information and we just turn on, I'm going to do floor deviation image. So the floor deviation image here, again, the image we were looking on, by the way, there's a cut. This is where the floor is being tested for if it's number one, kind of undulation, so you can see with undulations taking place, but also if it's above or below that 15 millimeters that we had typed in earlier. And this is why you'd want to rerun that. So let's just say the client expanded it to 20 millimeters or move the finished floor down so all they had was cut and no fill. You'd want to rerun the RoboFlat test so these CAD files get updated for you. But that proposed finished floor we were seeing on the Excel spreadsheet, once we move the floor up and down, that's where you get that number from and rerun this. So here, these areas are obviously, we've got to fill these areas and cut in the red, fill in the blue, and the legend on the right-hand side will tell you about that and try to help you understand where we're at with how much deviation there is. The next image, though, is the curvature image. It's a little more, it's something that a lot of people aren't used to looking at, but the remediation people will help them. Again, you can see, the construction joints really stand out very well. There's a column, that's what that white space is. But you can see the construction joints stand out very well. It's taking the normals of all the triangles, and as the triangles dip towards each other, those normals start facing each other, and the image is colored. Each one of the separate triangles is colored by the curvature amount. So you'll start seeing you can tell the floor is kind of undulating, and dips and things like that are taking place. So that's what that's about. If we turn on the all the floor curvature testing, I'm going to turn off that image. Then you'll start seeing all the floor curvature testing come up. And I think I missed one. I did somewhere. There it is. Oh, my origin, my vector here. So again, these are 2 meter long in this case because we selected a 1 meter test, which gives you a 2 meter overall curvature test. It does give you the percentage of slope coming in and out of that dip. And it also gives you on the highest side, the cut will always be cut for curvature because you only test for concave and not convex. So on the high side, we've got the cut. And if I turn the contours on, actually, we'll see that is the high side. Go back to floor deviation, and we will turn on our contours real quick. Sorry. There we go. And so the contours, you can see there's a dip here there's a -6 millimeter. You can see that dip going through there with those contours. And then we're coming up, and we're up to 3 millimeters positive right here. So you could tell that's a dip there. And of course, you'd want to cut this high side down because the remediation team, they struggle to make sure they don't make new problems as they cut the floor or fill the floor. Most of the time because fill is very difficult because of the product not standing up to robotic traffic. But anyway, the contours really help you see what's going on there and help the remediation team understand that they're going to cut all the way through here and try to get this tied in, and probably go ahead and just make a loop because they're using 36-inch pads, and to make a loop to try to smooth that whole heel off there is what they're going to do in that instance. But again, really this is all about getting your sheets built and getting this information in front of your client quickly. And here we're showing all the the cuts. So there's quite a few cuts on there. I'm sorry, curvature failures for that. So that's just a quick overview. I know I'm going quick, but that's a quick overview of the AutoCAD file that gets turned out. And then we'll go back to our list. The PLY file. So if you are interested to see what the surface looked like, what was returned to you, or what was used on our calculations, that we do triangulate a mesh for you and return it so that you can open it up with any mesh viewing software. And here I've got it open up in one of what I typically use, and I went ahead and colorized it by deviation again, just where you can see it. But this is a full 3D mesh, and it shows you, you can get a good idea of what the overall calculations were used. Some areas you'll see these little bitty white spots, and that's just because your point cloud was not as dense as it needed to be in that area. So the triangles didn't span larger than we have certain algorithms that we run through to make sure that we're giving you good test data. If we find areas where your point cloud is just too sparse, we'll go ahead and skip that area because we don't want to give you bad information. We'd rather work on the conservative side of things. So anyway, this is a full 3D model that gets returned to you for that. Then there are a couple other Excel spreadsheets. One, failure totals. Some of your clients, and again, this is back to trying to get your quick answers for your clients. Here, it just gives you a real quick breakdown. And this, a lot of times, we'll just send this an email. Hey, by the way, we finished your testing. And with the test thresholds, and here's our thresholds. This is how many failures you had on your floor. Gives them a real quick look at how many failures took place on the floor. And then the other one are the actual failure entities. And here, surveyors can get creative, and you can plot these on any types of maps that you want or anything like that. It comes back with the X, Y, and meters for coordinates. It tells you what your test result was from the I'm sorry, over here to the left, by the way. This is floor levelness testing. Here, as we scroll down, you'll see there's floor flatness and all that stuff. They're all labeled. So you could just import this if you wanted to into another product And so you have all this at your fingertips. There's floor flatness failures. This is the median point of the test. This is the result of your test overall. This column is your threshold, and then this was the resulting cut or fill in millimeters in this column. So you can use that to develop something real quick to return to your client. The other step, let's see, the deviation PNG. So these are the two images that we keep seeing inside AutoCAD. They're also sit right here, and they're referenced into this DXF file. It's important that those stay in the same folder, or if you want to move them later and then just re-reference them. They do have a world file with them. So if you're using a product that reads world files, then you can just stick it, you can just open the drawing up with the world file, and it will put it back to the correct coordinate system in other products other than our DXF file there. So it just depends what you want to deliver in. The last thing we do deliver is the grid points, a 300 millimeter grid point floor. We have clients ask us sometimes, well, yeah, that's great, you did all that, but we'd like to see the data. Back to the Excel spreadsheet we talked about, there is the raw data at the end of here that you can give them, or give them the spreadsheet and say, there's your raw data, do anything you would like with it. Sometimes clients like to check you, but then, or your calculations and things, but also this 300 millimeter grid DXF is exactly it. It has a point plotted and the elevations, I think, in meters here. It'll hopefully open up in a second. They're rather large just because lots of points, right? Depends on the size of your floor. I think this one was, 170 meters by 170 meters or something like this. A pretty large floor, to say the least. If we zoom into that, you'll see that that's what we got is, it's published to the meter, and published in meters to the millimeter, sorry. And so there you've got, and they're also published in 3D. So it's really easy if you want to generate your own surface from your own piece of software, because you wanted your contours to be different, a different size again. You have this once RoboFlat returns that information to you, so you can generate that off your own data. And really that concludes that portion of it. I've kind of run through all the deliverables there. And of course, when at the end, I can answer any questions about that as we go.
Thanks, James.
All right, you're welcome.
All right, I will have just a few more slides, and then I would like to open it up for questions. In just the end result of the outcome of this particular project that we did for the client is we identified all the flatness issues. The remediation company was able to know exactly where to go to address the issues, and the warehouse was prepped for the robotic system installation on time. Using RoboFlat gave us a wide variety of benefits. It eliminated multiple pre-processing steps for us, freed up our surveyors' computers, since it's performing in the cloud, so they were able to use the computer to work on other high priority tasks and save multiple hours in testing, really streamlining the testing process. So just quickly, key features to RoboFlat is it is a cloud solution. It tests the entire scanned floor, delivering comprehensive, as we've seen from James's presentation, comprehensive testing results very quickly. It can handle data from any 3D laser scanner, so you're not tied down to a specific manufacturer. And it delivers advanced precision, and it's built to be scalable. So we know that these point cloud, especially for large floors, these point cloud files can be massive, and RoboFlat is designed to process a large amount of files very quickly. So the benefits, I think this is the last big slide I have, is with RoboFlat, we found contractors can easily provide this testing with scanning services. The concrete remediation team also benefited from RoboFlat by knowing exactly where to fix the floor issues. The building owners had peace of mind knowing that their floors were being built correctly. And also the robotic system manufacturers had that peace of mind knowing that their systems were going to be able to run smoothly on the finished floor. So we do want to encourage questions. And we just started with a few to kind of get the questions flowing. The first one is, where do I access RoboFlat? As I mentioned, RoboFlat is an online solution, so it is part of our Bricks platform. The URL is gobricks.com. Maybe Jay, you could put that in the chat. And you can see, let's see, actually I pulled it up to show you here. If you go to gobricks.com, you can start a free trial immediately with your own data. Are there any, some of these questions I'm actually going to rely on James as well. Are there any floor size limitations?
Yep. Yeah, there is right this second. We're at 300 meters by 300 meters.
Okay.
That doesn't have to do with file size. That really is the overall floor size. And that's so it may be a 30 gig file, but it's just the limitations of the actual size of the floor. So we just break it up into sections. If we get actually we hadn't crossed that yet. 300 meters. I don't think we've gotten larger than that. So usually what happens on the bigger buildings is they pour half the floor, or they'll pour it in quarters, and we'll go out there and check it in halves. So half the floor will be less than 300 meters. I don't think we've ever run into that problem yet. So
very good. And how long does testing take, the actual analysis, the RoboFlat analysis? It really depends, I think, on the size of the file. But James, do you know? I would.
Yeah. It's usually, so for the smaller buildings, I say smaller, we're 100 meters by 100 meters or something like that. It's less than 30 minutes. To the really big ones that are pushing that 300 meters by 300 meters, if it could also be, and also the size of the file, like you were saying, if it's 15 gigs or so, 15, 30 gigs, you could be an hour and a half on that. Much faster, by the way, than our local system that we had developed to do this, because you spin up so many instances and process away. So much faster online. And the good thing is that hour and a half, we are off doing our next project or getting the sheets ready or whatever it might be. But now I've freed somebody up.
Right. What file type is supported? So RoboFlat accepts E57 files, and you've seen what types of files it outputs, it generates. And does RoboFlat come with a subscription? Yes, it does. So it's a very cost-effective way to use RoboFlat. We also have a pay-as-you-go option. So we wanted to add as much flexibility to the licensing model as possible. So with that, I would love to open it up to if someone wants to raise their hand or have any questions.
Got some in the chat, looks like.
Oh, great. Okay, let's see.
Okay.
Do we have, thank you, Mustafa. I'll read your question. Do we have control points? Can we mark low and high areas on site?
Yes. So what we typically do is we go out and does the GC already have a benchmark on site that they've been using to develop their floor as they poured, the construction? We're out there after they poured concrete. So typically, yes, they have a benchmark. So we'll make sure that our scans, we will also include that benchmark in our scans. But we also, and this is, it depends on the surveyor or how they approach it, but we also take a digital level with us, and we'll run levels around the site and also set survey control around the outside. This gives us the ability, if the client so asks us to, we can go back and stake out these CAD files. We can take these CAD files, take those coordinates, dump them into our robotic total station, and stake out all the failures on the floor and mark them, which we've done before, marked them with kill, so that they're easier to find, and also mark high and low spots. So absolutely, that is something that can be part of this process, and it's important. I'll back up real quick. So it's important that what we make sure we do with our point cloud is when we're registering it, when we're reducing it and producing it, we take that and we put it onto the client's CAD files. So we ask the clients, hey, can you give us your design files for the floor area? So we'll put our point cloud, we'll use the columns and best fit all the columns to our point cloud and get onto that coordinate system. Then every report that we send the client in a PDF or CAD format, they can reference into their drawings. Their teams can all reference it. Everybody can, and everybody's on the same coordinate system. And immediately they can see all their failures up the chain, and they can give it, throughout their project because we're on the same coordinate system with all drawings that we deliver that are based off of that cloud.
Thanks, James. Mustafa, I hope that answered your question. Samir has a question. Does come up with overall numbers, and then which ASTM will cover this method?
Yep. It will run, when you run your regular ASTM, you can put in the failures that you're looking for, the overall SOV and things like that for the floor, and it will return Excel spreadsheet with the overall floor failure numbers that your client often asks for. Hey, what's my ASTM? Did I pass or fail the required testing? And you will get the yes or no on the pass or fail and the numbers that return to you. And also in the Excel spreadsheet, a CAD file comes along with that. And each one of the runs are shown on the floor that were generated automatically. Now, the good thing about our ASTM product is that you don't decide where those runs go. It's an independent check in that case because you can't move the runs over a foot to make them pass. They're going to run where they're going to run for your ASTM testing. And you're going to come up with pass or failure on each one of those runs. Now, one thing we do is we over-test some. So you will have, if you were going to have in one column bay, you would typically have 4 runs in that for the ASTM. You may get, depending on the size of the column bay, you may get 8 runs. So you can pick and choose and delete the runs that failed and only have passing ones, or you can turn off all the passing ones and give them the failures to your remediation team to have them go try to correct those runs. And so that is there for you. It's kind of we do over and above ASTMs to give the client, the final user, the GC, and the remediation teams more information because ASTM is very sparse compared to what we're doing here. We're trying to do high-end robotic floor testing, and a lot of times so that you get these super flat floors. So a lot of times ASTM, it'll get you close. It'll get you close. Your concrete contractors will lean on that heavily to try to pass those FF and FLs, but they will not. For free flow traffic of robotic systems, they often are not good enough for those specifications for the robots to run correctly without clashing with each other as they pass because they're passing within millimeters at high speed. So these other custom testings in TR34 and things like that are used, and that's why a lot of robotic manufacturers, they call out the ASTM for the overall warehouse build, but then they say, hey, but in my robotic field, I need you to pass these other specs, which you can automatically type. You can type those into custom and be able to test that. Hopefully that covers it.
Thanks, James. Are there any more questions?
We'll take one more questions. All right. I guess you guys need to a little bit sorted out our information. We gave a lot of good information today. So that being said, I'd like to introduce about how we can continually communicate if you wanted to try out, if you want to learn more about RoboFlat. So we share our website. Please go to the gobricks.com. And also, if you have any questions, please reach out to us, as you can see here. And my name is Jay Kwan. And also, I'll be sending a personal email to you. And we can also set up more of the customized Q&A sessions that is more geared toward to your own projects. So I'd like to say thanks for everyone to join in, and especially thanks to Kathleen and James to present today, and we're looking forward to talk to you more. Thank you.